Hello everyone and welcome to part 3 of implementing the neat algorithm in Java. In the first video, it has been quite some time, so I'm just gonna recap what we did. In the first video we made all the genes and set that model up. In the second video we made a crossover function for breeding genomes together. We also made a few mutations, and that's it. In this video, we're gonna write an evaluator that will take a population of genomes and then evaluate them, see who, give them a score, a fitness, and then we're gonna take the best ones and generate a new generation from that, from crossing over the best genomes from the previous generation. And how that is going to work exactly and how neat specifies that we should do it, we're gonna talk a lot about in this video. We're still not simulating the actual networks. That's gonna be next video. Okay, but I think this video is probably gonna be more interesting than actually simulating, because we are gonna see some results. Okay, let's get started. This right here is the evaluator that I have written. It is an abstract class, and it is also long. It's a big class. It has 3 nested classes. It is a bit, it's big. That's what I'm trying to say. So I think we're gonna break down what this is and what this does using pseudocode. So right here, this is what I initially thought this should be. A class evaluator with the void evaluate, and then this evaluate would perform calculations for one generation. So now we should think about what happens during each generation. I switched over to Notepad++ here for the syntax highlighting. I've added some pseudocode here to the evaluate so we can see what happens each generation. First off, we place genomes into species. You remember in the article, they talked about how all the genomes should be grouped into species, and the score should be divided amongst each member of the species so that a larger species cannot reap the rewards of having many networks perform very well, whereas small species of 1 or 2 would be at a disadvantage. So the first thing we do each generation is place all the genomes into species. The next thing is evaluate genomes and assign fitness. This is the normal evaluation of the network. This would be where, in a game simulation, this would be the actual simulation. If you have simulated networks, then this would be where you take your genome and make it into a network and test if the network does what you want it to do. And actually a good way to do that, I think, is to make this evaluator, this class, abstract, and then add an abstract method for evaluating a genome. We can do that right now really quickly. Like this. So whenever we want to make an evaluator, we have to also implement how the evaluator evaluates all the genomes. Oh, and this should not be a void, this should be a float, because this would return the fitness of the genome. Alright, that was step 2 in our natural selection algorithm here. The third thing we do is put the best genomes from each species into the next generation, just automatically, without any changes. This means that our population, the best individuals in our population, cannot get worse as time progresses. This is to protect against the best individual being bred with another individual, creating an offspring that is not as fit as the parent. This way, the most fit individuals, or the most fit genomes, will always be transferred automatically into the next generation, securing that our fitness will never go down. Great. The last thing here is breed the rest of the genomes. We're going to have a population size, and this, let's say it's 100 for one generation. Then the next generation rolls around, and we have 10 species. Then the best of each species will be transferred to the next generation. If we have 10 species, that means 10 individuals. If our population size is 100, that means we now need 90 more genomes in order to fill the population. And that's where breeding and crossover and mutation comes in. Before we actually can go on and implement this evaluate function, we need some tools. And one of the things we need is the notion of a genome that has a fitness assigned to it. And giving the genome a fitness value would be to mess up the model in my mind, because the fitness is contextual. It can change. It's really depending on the situation. It doesn't belong in the genome class. That's my argument here. So what I've done is I've made this fitness genome that just encapsulates a genome with a fitness. And in order to keep this super short, I have omitted setters and getters. I've just exposed these two fields inside the fitness genome. Great, that's the first thing we need. The second thing we need, now that we have the fitness genome, is this fitness genome comparator that will just compare fitness genomes with fitness genomes and return an integer, basically. And this means that we can use the sorting functions in the collections part of the Java language. So this just means that we have now a way to compare two fitness genomes, and we are comparing the fitness, so we can sort them. Whether or not this is actually needed, I'm a bit unsure. I think we could actually do it without, but we can discuss that in the future. For now, we're gonna get it. Now the last tool we need before we can get started in the evaluate method is a species, an object representing a species. And in need a species, just a list of genomes, and then a mascot to represent the species. And whenever we check whether or not a genome belongs to a species, we check the genomic distance to the mascot of that species. And every individual inside that species will have a small genomic distance to the mascot. And each generation, a new random mascot is chosen. So here's the code for that. We have a mascot genome, we have a list of genome members, and we also have a list of these genomes with a fitness attached. This is going to come in handy during calculation. When we create a new species, we give it a mascot, and then we add the mascot to the member list. That's really important. The mascot exists both up here and also in the list. All right, that's it. We can now progress. Oh, we still need some things, actually. We need a way to get a species from a genome. Now we shouldn't put the species inside the genome because the genome doesn't have a species. It belongs to a species, but we still want to have a way to look up what species a specific genome is in without having to look through every member of every species ever. An easy way to do this is to make a map. So I'm gonna make a map really quickly. Great, this map allows me to, whenever I have assigned a species to a genome, I can put the genome in here as a key and the species as a value, and I can always ask and in constant time get an answer for what species does this genome belongs to. Great, the other thing, or the last thing, I think, is is a way of getting a score from a genome. I know we have kind of touched upon that down here, but if I just have a genome, how do I get its score? I can't do that right now. I either I have the genome or I have the fitness genome. So just to make that possible as well, let's make another map. Great, we now have a map to store our scores in, our fitness values in as well. Great. I realize now this evaluator is probably not very memory friendly. Let's fix that in the future. Let's make it work first and make it work better in the future. All right, I realized the redundancy here. Oh, maybe we should have a list of species as well. That's an original thought. Private list of species. Species. There we go. Species. Okay, I think we are ready. I think we're ready to jump into this evaluate method. It's gonna be a little bit quick. Be ready to pause the video at any point. Place the genomes into species. That's the first thing we're gonna do. So we're probably gonna loop through all the genomes, right? And we're probably gonna, for each genome, check if there's a species currently that it could belong to, right? So we probably also want to loop through the species as well. Great. Now we also want to make sure that we can keep track of whether or not we have found a species. So we're gonna add a boolean here. Found species. Make it false. Great. Moving on. For each species, we check with the mascot if our current genome that we're checking is within a reasonable genomic distance from the mascot. If this is the case, then the genome belongs to this species. So here this is a static method, compatibility distance. We check the G, that's the one we're currently checking, against the mascot of the species we're currently checking. This C1, C2, and C3 are constants. Let's not worry about those right now. And dt is the distance within, or the max distance that can exist within one species. So if the compatibility distance is less than this, then the genome G here is going to belong to species S. And we're gonna add the G to the S's members. That's a bit hard to follow maybe. The map species here, that should be the species map. That's what I mean, species map. So we can always go back and look. Great, and we mark that we found a species and we break exits this loop, so we're down here now. What can happen down here is that we checked all the species and there wasn't one that was suitable. So in this case, we make a new species where this genome is the mascot. So that's what I've done here. If we make it down here and we haven't found a species, we make a new species, and we also put that in the species map. Great. I think that is it for placing genomes into species. Now every genome will belong to a species. Awesome. Now we make it down to evaluate genomes and assign fitness, and this is where we realize that we forgot some functionality down here in our species, because when doing this, it is best if we can gauge how well a species is doing. We want species that are doing very well to produce many offspring, and species that are not doing so well to produce fewer offspring. So how can we make sure that we know how well the species is doing? Well, we can add a tally of the members' adjusted fitness. So that's what we're gonna do. Great, the total adjusted fitness. And then we're gonna add a method for adding fitness to this species. We're gonna call this method every time we evaluate a genome inside the species. And in this way, each generation we can actually check whether or not a species is doing great or not doing good at all. Here it is, the method add adjusted fitness. It just adds it up. Great. Now, this structure is beginning to look like something that would need to be reset after every generation. So let's add a reset method. Great, there we are. To reset, we do 3 things. Right, we clear all the members because we assign species each generation, right? So we clear the members, and the fitness population, which we haven't even gone into yet, we also clear that. And the adjusted fitness, we clear that, right? And we select a random member to become the new mascot. So now we have better species, right? And we can go on to evaluate genomes and assign fitness. To do that, we should probably also loop through the genomes yet again, right? So that's what we're doing. Right away, we also get the species, so we know what species does this one belong to from the species map. And then we evaluate the genome using our abstract method down here. Gives us a score. Then we adjust that score because genomes are competing within niches within their own species. This is part of the need method. So the score must always be divided by the amount of other genomes in the same species. Now, we want to add that using our new method to the species adjusted fitness, so we can keep track of that. Then we also want to add, since we now have given a fitness to this genome, we want to add it to the fitness population. That's the fitness genomes inside the species. And we just make a new object here with the genome and the adjusted score. Great. So inside the score map, we also put the genome and the adjusted score. The score map's up here. Awesome. Now, if the score is the highest score, we add it to the high score. Let's not do that right now. That doesn't matter right now. That's just a way for me to keep track of who's best inside the real class. But it doesn't really matter. So let's do this instead. Great, that's evaluate genomes and assign fitness. That's how we do that. Awesome. Now we can move on to put best genomes from each species into next generation. This should... There's 2 ways as I see it to do this. You can either sort this structure, this fitness genomes. We can sort it really easily. We can sort that inside each species and then get the first index. Or we can loop through all of the fitness genomes and just keep track of the best one, and when we're done, take the one that has the highest fitness. This class has been rewritten so many times that I am a bit nervous about not sorting that list option. So that's what I'm gonna do. It's really simple. We go through the species. We have this collection sort function here. The fitness comp is just an instance of this fitness genome comparator with the compare. Great, we are here. Now we reverse the list because this will sort them in ascending order because that's the natural ordering of numbers here in our universe. So we just reverse it really fast. And then we take the fittest genome from the species, that's going to be at index 1 here, and then we add that to the next generation genomes. We add the genome to the next generation genome. I don't know if we have a list yet for the next generation genome. We don't. Let's make that. Next generation genomes, there we are. The plan is here at the very end, we take the current genomes and then we point that to the next generation genome. I'm just gonna do it. And the reason for this next generation genomes is that we can just at the end here of the generation say that our genomes are equal to our next generation genomes, and then the next generation genomes are gonna be just a new list of genomes. There's probably better ways to do it. I think if I had two temporary lists, I could just swap between the two, but this is way easier to understand. So let's make it work, let's make it better, let's follow that. Great, so we only need really to breed the rest of the genomes here. Cool, man. So right now, our next generation genomes are not gonna be as big as our current genomes because we have only added the best from each species to it. So we're gonna have a loop that looks something like this. We want it to loop as long as the size of the next generation is smaller than the population size. So we want to fill up the next generation to make it as big as the population we want. Now I'm gonna select a species that will breed a new member, and that species should be selected based on how successful that species is. So how large their adjusted fitness is. The sum of the adjusted fitness in the species. I have this method to do it. Get random species biased adjusted fitness with an error in it. Great. This method I'm gonna copy in here. It works by summing all the total adjusted fitness of all the species and then choosing a random number and looping through the species until we meet that random number. And I don't want to go into it more than that. I have a very similar method where we pick a genome from a species based on the genome's fitness. I'm gonna copy that in as well. Great, that is here. Get random genome biased adjusted fitness. It works in the exact same way. Goes through the fitness genomes in the species that we select from, sums up all the weights, gets a random number, goes through them again until we meet the number. Awesome. We're gonna use these to get the two parents from this species. You see, now that we took care of these two ways of selecting a pseudo-random element from a list, we can now just get two parents. We don't have to make our head spin with So now we have an easy way to find two parents where genomes that are more fit will be more likely to generate offspring. Now we only need to do crossover between these two parents to create a child genome. Great, that's what we're doing here, the genome child. Now we look at the score map for each of these parents. We look them up in the score map to see who has the highest score, because in the crossover function, the first argument here should be the more fit parent. So if this P1 parent has the highest score, then we call the crossover function with the P1 as the first argument, else we do it the other way around. That's the only reason for that. In the end here, we should just add the child to the population. Great, and there's the child added to the next generation genomes. Now, that's just the crossover. We should also have a way to mutate. We have 3 different mutations that we implemented, so let's use them. And here is a block that does just that. We have a mutation rate. If we hit a float that is smaller than the mutation rate, then we do some mutation on the child. If we get a float smaller than the add connection rate, then we do a mutation where we add a connection. We also have this mutation where we add a node. So now we're pretty much done with this evaluate method. Awesome. There is a few things we need to tighten up here in our evaluate method before we can use it. It is not intuitive, but hopefully you will have an understanding for it. When we call this evaluate many times, the species, they persist between generations. There's a chance of a species becoming dormant. So whenever we have placed all our genomes into species, we should make sure that each species is still active and has at least one member, because we will see these species that have no members. So I have used an iterator for this. An iterator is a way to go through a collection while being able to modify the collection. We can't do that with this type of for loop, but we can do it with an iterator, with this iter remove. So if the species has no members, we just remove the species. Another way to tackle this would be to iterate through the species in reverse. That would also that is a valid solution, and I think the solution that the coding train uses all the time, for what I've seen. But you can also use an iterator in Java. The second thing we need to tighten up here is the score map and the species map. These should be cleared after every generation so that we don't have any genomes matched to any species when we begin our evaluate method, and no genomes have a score assigned to it when we begin our generation. Likewise for our species, because they have this fitness genome list, this should also be cleared in our reset. So we should also reset every species before we begin a new generation. So right at the top here of the evaluate method, I'm going to reset all the species, reset the score map, reset the species map, and reset the next generation of genomes. And that's it. That's the entire evaluate method. So now we have built an evaluator that hopefully works. We'll see if it works in a second here. This is all pseudo code. I'm not sure if this version of it actually compiles. So let's jump into Eclipse, where the actual code lives, and have a look at it. And hopefully it won't be as overwhelming as if we have just jumped into the class from the beginning. So this right here is the evaluator class in Eclipse, the version that compiles. You'll see I have a few more variables, a few more fields here in the class that we had in our notepad document. I'll try to explain that. We have the fitness genome comparator, which we're using to sort the list inside the species. We talked about this. These two counters here are the innovation number generator, so we can keep track of corresponding genes. We only use these for when we are introducing new genes through mutation. You'll see down here in the evaluate void that down here, when we breed the rest of the genomes out, when we add a connection, we need to have a connection innovation number to attach to that new connection, and we just give the method the counter so that in here we can, let's see, over here, when we make a new connection gene, we have a new innovation number for it. Same down here with the add node mutation, but in this mutation we're adding a new node and two new connections, so we need both the connection innovation generator and the node connection innovator. So that's those. The random is for randomness, and these are constants for this is for genomic distance, and these are for mutation. These are mutation rates. Maybe these shouldn't live inside the evaluator. Maybe we'll fix that in the future. The population size is the population size, the genomes, and then these ones you know. I also have the highest fitness, just so I can grab that from outside the evaluator using a getter. We also have the fittest genome, just so I can get the fittest genome from a getter. And that is about it. You will see the evaluator method is very close to what we made in the notepad. Then we have these ways to get a random species and ways to get a random member of a species. Then we get the amount of, this is just some getters so I can keep track of my evaluator as it is running. We get the amount of species, and we get the highest fitness, and we get the fittest genome. Then we have this abstract method for the evaluate genome, then we have the fitness genome, the species, and finally the fitness genome comparator. So this class, you now know exactly how it was made. Great! Let's test it then. Let's see if we can test it and see that it works. To test the evaluator, I have written these 3 test evaluator classes that we will have a look at. Let's have a look first at the test evaluator many connections here that I've opened. It just has one main method, and it creates a genome. Oh, maybe I should have talked about this. In the evaluator, in the constructor, we give it a starting genome that we will just fill the population with copies of this one genome. That happens down here, where the genomes is filled with new genomes that are made using a copy constructor from the starting genome. So we will get different objects that are just completely identical. Great. The evaluator is custom, since it is the evaluator is abstract, so we can't just make a new copy of it. We need to provide this implementation of the evaluate genome method. And in this case, we're just giving it a fitness depending on the size of the connection genes list inside of it. This means that networks that have more connections will have a higher fitness. It runs for 100 generations. Is that correct? No, that's not correct. The population size is 100. And then down here, we run it for 100 generations. We call the evaluate, and then we have a look at the evaluator, the highest fitness, the species amount. And we also, every time we have gone through 10 generations, we print a copy of the network to this folder here, connection amount 1, that I will open in the System Explorer here. Great, we're now inside that folder. So let's run this class. The many connections test, proceed. And we have an error. Why do we have an error? Okay, I believe I have fixed the problem now, the bug. Let's try to run this. I have the folder open here. Let's run the test, proceed. And we can see it run in the generations here. We have very, very many species, and our highest fitness is still growing. We're going for 100 generations here. Our amount of species has kind of plateaued. The fitness is still going up. And we're done. Let's have a look in our folder here. We have images of our 10 different networks. Let's have a look at how they developed. This is the starting point here. This is the network that I gave the evaluator to begin with and just filled the population with. We can see here that it got some more connections, even more connections. As we progress forward, we just get more and more connections in these networks, because that is what they were rewarded for doing. Okay, so this test is a success because the networks, they evolve the way I want them to. The next test is this one, where the network rewarded for having small genomes, or small number of connection genes, I should say. This also runs for 100 generations, and it has a population of 100. And I think for this one I want to change the parameters that we're running with. This dt, maybe we're gonna put it down to 4, maybe 3, to make sure that there's not much diversity within one species. This means that the crossover will happen with networks that are only that are more similar than before. Okay, so let's find the folder here. Connection amount 2. Connection amount 2, show in System Explorer. There we go, it's currently empty. Great, let's run the test. Proceed. And right away we get 100 species. That is because I put the dt down, so now if there is not a species that fits for a genome, it will create its own new species. And if there's only one individual in a species, that individual is guaranteed to progress to the next generation, as we take the best genomes from each species. So a way to combat this is to increase the dt. We pretty much get this same fitness of 500 all throughout, and that means there are only 2 connections. But unlike before, they will not evolve towards having more connections. They will evolve towards having as few connections as possible. And since this is the starting point and there's no way for them to get any fewer connections than this, all the different generations will just find the same solution with these 2 genes. So awesome, something different happened than the other tests. So it's not just the case that my program will always just spawn these large networks. Okay, the third test here is the 100 sum, where networks are rewarded for having a sum in the absolute value of their weights be exactly 100. So the farther they are for 100, the smaller their fitness will be. If the weights combined, the combined sum of all the weights is 100, that will give it a very high fitness. Let's find the folder down here, output connection sum 100, show in Explorer. It's also empty. Okay, great. Let's run this. Oh, and we almost get a fitness of 12 right away. Oh, and this will run forever. And our amount of species is again going to 100, so I think we should increase this again to maybe 10. And let's have a look at the history here. How quickly did it find that solution? Generation 0 has a fitness of 10, and then it goes up slightly, and then it stays there. Since I think it stays there as there are so many species. Let's have a look at the networks here. It doesn't appear to be the case that these combine to be 100 at all. Weight sum is 23. Okay, there we go. So it didn't actually find any optimal solution, and I think the reason is this there's way too many species. Let's try this again. Yes. So we see the number of species is not increasing as rapidly as before, but the fitness is increasing, has increased way more than it was before. The weight sum here is 99.999, so I think that is pretty close to 100 if we're ever gonna see exactly 100. So it has actually found a solution to my problem. Let's have a look in the folder. Can see after, what was it, after 10 generations the fitness is at about 11. Oh, that's the wrong one. Where is it? Let's find it again. There we are. This is the 10th generation. It's not that good. And then the 20th. How good is the 20th? It has a weight sum of 48. So that is better. And the 30th generation has a weight sum of 99.9, so that's already pretty much as good as we're gonna get. Now how did it solve this? By having an 8 weight and a 52 weight and a 29 weight, so that combined is close to 100. Let's see if it's the solution it sticks with. 22 and the 28 or 52. It seems that this network is, oh, there's a change there, down to the 47 with a 4 and some other numbers. Great. Now this one is a bit closer with some other weights, but we can see that it solves the problem by having a weight sum very close to 100. So it looks like the evaluator is working, so that's great. And I think in the next video we're gonna start working on simulating the networks so that we can make them control AI in an environment. So that's hopefully gonna be interesting as well. Thank you for watching my video. Welcome to the very end of this video. This takes a while to edit. There's just so many cuts in this. The recording is quite long to begin with. So I am going to ask that if you made it here, please consider leaving a like and please consider subscribing. I'll see you in the next video, hopefully soon. Thank you for watching.